Our app also relies on a number of backend services, and within the AI and data department, my focus is the Python side of a broader stack we built together with our ML colleagues. So now that the brief moment of blameless self-promotion is over and we can get to the point. Originally, I picked up PIP audit on the advice of a colleague from security. So, Max, if you happen to be watching this, hi. And this talk consists of three main parts. The first part is what PIP audit is and why it matters. The second is about real vulnerabilities, not just from 2025. And the last one is actually about how to live with it daily. So, just a second. Yeah. So I'm approaching this as a practical engineering talk, not as deep security workshop. So because of the time slot, I'll simplify a lot of things. So security folks in the audience, I know that I'm cutting corners. Please bear with me. I hope that it keeps the talk simple and clear. So I ran PIP audit retrospectively across about 50 internal repositories, not because we had some incidents, but because I wanted to see what we would have been exposed to if we hadn't been patching. So most of what is found wasn't actually exploitable in our context, and I picked the most interesting ones to look at the problem from different angles. And let me start from the defining what I mean by supply chain here. In our context, supply chain security is the idea that your service is not just your code. It's also a long chain of other people's code and tools that you implicitly trust. And believe me, every one of us trusts far more things and far more people than we usually realize. We trust the Python interpreter itself, and unless we are writing a script using nothing but the standard library, we were easily pulling packages from PyPy, and Python is famous for its ecosystem for a reason. So that is the supply chain part, a long chain of code and tools that we trust, often implicitly. And once you see software that way, the next question is, how do we talk about problems in that chain? So that is where CVE comes in. CVE stands for Common Vulnerability and Exposures. It's a standard way to refer to publicly known security vulnerabilities. And you may ask, why should I care as a developer? First, because if you ship it, you own it. A flaw in any of your dependencies is still your production problem, not the vulnerable packages maintainer. You may also care because you only know your context. CVE score alone doesn't tell you whether something is actually dangerous for your service. And because fixing things is faster and cheaper, in CI it may be just a small update, but in production it can become an incident involving a lot of people, including your clients, for example. And for sure, because you already making trust decisions anyway, and PIP audit just makes them more visible. So where does the data come from? For PIP audit, the main source is a Python advisory database from PyPA. It's a Python-specific vulnerability database. It was historically seeded largely from national vulnerability database data, but PyPA normalizes and curates advisories for Python packages and exposes them to tools such as PIP audit via PyPy's API. And what matters here, that because vulnerability data is no longer coming from just one universal place like NVD. In recent years, NVD has faced enrichment backlogs, so more ecosystems maintain their own advisory sources, and the system becomes more distributed itself and more decentralized. And through this talk, the main number you will see is the CVSS, and it is severity score. It's a score from 0, which means good, to 10, which means awful. And it gives you a rough idea of severity, but not necessarily the priority for your service. There are also other useful metrics like EPSS, which tries to estimate the likelihood of real-world exploitation, for example. But for the sake of simplicity, I'll mostly stick to CVSS in this talk. And yes, in some sense, this whole talk could have been just a link to the PEEP audit README. For sure, it has a great documentation. Because it's basically the simplest way to ask Python project, do any of my dependencies have known vulnerabilities? And just it. You run again, you can run it against your environment or dependency file, and the tool gives you a list of findings. The output contains usually version, CVID, package name, fixed version, and supports machine-friendly formats also. PEEP audit is the Python, I would say, native zero config starting point for security. If you need multiple language support or more enterprise-style capabilities like container scanning, license compliance, CPSS-based prioritization, then for sure you need other tools. And one more important limitation, this is not a tool for catching malicious packages. This is a totally different problem, and PyPy is constantly working on that side too. For example, by removing malicious packages and enforcing the security of the PyPy itself. So far, let's move from the theory. I will tell about what PEEP audit actually found when I ran it across real internal repositories. The first one is the most funny because for sure PEEP also contains vulnerabilities. These were not critical on their own, but there were bugs on how PEEP handled packages and extracting archives, and that is enough to illustrate the point. The tooling itself can be part of the problem. So even the tool you use to install packages may also be vulnerable. That is a useful reminder that the supply chain is not just your application dependencies. It also includes the tooling around them. The other example is urlib. It's a good example of dependency you may never import directly, but still end up shipping in production because it sits deep in the Python HTTP stack. So once I ran PEEP audit across many repositories, it started showing up again and again. In this case, the bug was simple. If a server sent back a specially crafted compressed response, urlib could keep decompressing it until your process run out of memory, and basically it's a denial of service. At that point, the problem is no longer just technical, just because it becomes organizational too. How quickly do you notice it? How many repositories are affected? And how consistently you can roll out the fix for everything. So the lesson here is simple. Small, very boring, very common transitive dependency can turn into mass-scale issue surprisingly fast. H11 is an even better example of invisible dependency. You may not see it in your dependency file, but it still shows up in production through packages like UVcorn or HTTPX. So I think that you know them for sure. Here the bug was in how H11 parsed chunked HTTP request bodies in some setups that could make H11 and a reverse proxy disagree about where one request ends and another begins. This is called request smuggling. So one layer of your application sees one request and then another layer too. And that means a hidden second request may bypass controls and break the security of your application. So again, the point is simple. You can inherit serious risk from a package you didn't even know you are shipping. Authorlib, to be fair, authentication is hard. This is not some easy corner of engineering where you can usually get things almost right. In fact, it is one of those areas where the usual advice is the opposite. Never implement it by yourself if you can avoid it. Use well-known libraries, standards, and boring defaults because the space is full of subtle failure modes and you don't know them all to implement it cleanly. So when libraries like that break, the impact is not abstract. It can mean forged tokens or broken authentication in your environment. And in this case, it wasn't just one CV. Over a short period, Authorlib kept accumulating them. Token forgery, alg-known, decompression bombs, padding oracle issues, and any one of them, would already be bad enough on its own. The real problem here was not just severity, but churn. You had to keep updating again and again just to stay clean. The takeaway is that for security-sensitive dependencies, patching is not a one-time event, it's a process. And Pillow was a good example of a risky kind of dependency. Libraries that parse and process complex file formats, especially user-supplied ones, tend to accumulate security issues also, and image processing libraries are very much in that group. This one was a memory safety bug in Pillow, especially crafted PSD file could trigger an out-of-bounds write while being parsed. So attacker-controlled PSD file can push Pillow to writing outside the expected memory boundaries, which is serious and can lead to crash or something worse. So let's imagine a service that only processes its own internal images in non-PSD format, so it has no external image source. In that case, exploiting a bug like this becomes much, much harder because an attacker would first need a way to get a crafted PSD or similar file into internal workflow, right? So in some cases, the vulnerability is real, but in this context, it is much closer to a patch on a schedule issue than to drop everything in emergency. The package is vulnerable on paper, but the vulnerable input is not realistically reachable in the actual service. Now let's imagine a service that processes user-supplied images. Suddenly, the exact same vulnerability looks very different. If attacker can upload files, and Pillow is part of that path, then a crafted PSD is no longer some exotic edge case. It becomes a realistic input to the system. And once untrusted input can reach the vulnerable parser, it stops being a background issue and starts looking like something you want to patch quickly. So here, the CV is the same, but the urgency is much higher. Not because the score changed, but because the path to exploitation became real. And finally, the clearest case, the service exists to specifically process untrusted PSD files uploaded by end users, for example. And if that service is running without isolation and under a privileged user like root or administrator, the situation gets even worse. You are feeding attacker-controlled input straight into vulnerable code with escalated privileges. So if a crafted PSD can trigger an out-of-bounds write in Pillow here, this is no longer just a theoretical parser bug on the slide. It's a direct production risk, and the priority is obvious: update now. What I'm trying to say here is when you see a critical score, that is not the moment to stop thinking and start panicking. If anything, it is the moment to start thinking more carefully and assess the situation with much more attention. Again, the score didn't change, the context did, and that is exactly the point. The same CVSS can mean update when convenient in one service and plan it soon in another, and drop everything and patch now in a third. So CVSS score alone is not enough. It gives you a useful severity signal, but it doesn't know your service, your inputs, your attack surface, and threat model. CVSS can help you notice the problem, and context tells you what to do about it. As for H11 or JSON, the bugs were very different. I have not really talked about or JSON before, but it's useful contrast here. For example, H11 case, it was request smuggling, and it was depending on surrounding setup. But our JSON was had an uncontrolled recursion issue with dumps and could lead to denial of service with deeply nested JSONs. In both cases, the CVE was real, but the practical risk still depended on the context. And this one is my favorite, even it's 2024, just because it won't fix. Cryptography is hard and is also another example of never implemented by yourself idea. And for sure, I'm not going to turn this talk into discussion of elliptic curves. But the basic idea is simple. The library leaked tiny timing differences while producing signatures. And over many observations, that can reveal information about the secret values used internally, like private key. The important part for us is much simpler. This was not the kind of issue where you see CVE and instantly know what to do. This was a dependency pulled in through Moto, its mock library to test against AWS. So right away, this didn't like an obvious production problem. In practice, the attack required thousands of sign-in operations and nanosecond level timing measurements. Against throwaway keys generated in memory during tests, that was not a realistic threat. And this is also what makes the advisory itself so interesting. The library maintainers explicitly says that side channel attacks are out of scope and they are not planning to fix it. And one of the references is an article about constant time comparison in Python, which is a nice reminder that doing constant time correctly in Python is in general a very suspicious idea. Take a look at this article, it's very interesting. So the takeaway is broader than this one particular package. Sometimes there is no fix and you still must understand the context and decide what to do. In the Moto case, this eventually resolved itself because the dependency of ECDSA disappeared. And then there was a nice ironic one. The auditor audits itself. The vulnerability here was not in our application stack at all. It was dependency which is brought by pip audit itself. So the very tool used to detect vulnerabilities also introduced the new vulnerability. The bug itself was a classic time of check to time to use problem. The code checked one thing, then acted a moment later, and that gap created room for the state to change underneath. And honestly, that pattern should feel familiar if you work with distributed systems. You deal with this kind of problem all the time. You check a condition, the world changes, and by the time you act, your assumption is already stale. That doesn't mean that the tool is broken or useless. If anything, it proves the opposite. Supply chain risk doesn't magically disappear just because you are using security tool. So the takeaway here is simple. Trust is recursive. Even the thing you use to inspect the chain is still the part of the chain. And trust is not a one-time decision. The package you trusted 2 years ago may now have CVS, a burned-out maintainer, or no maintainer at all, and pip audit is just trust but verify on autopilot. So let's move to part 3, because the real challenge is not finding the vulnerable package. I just want to talk about how dependency updates can fit into normal engineering work. So why dependencies don't get updated? Usually not because people don't care, but because updates compete with everything else. Business priorities, new features, and so on. Sometimes there are no tests in the projects. Sometimes the service is fragile. Sometimes nobody is sure who owns the repo anymore. Sometimes the update itself is technically small, but the fear of breaking production is large. And sometimes major version upgrades are really painful, and they really are. But that pain is often what technical debt looks like in practice. Dependencies drift apart, old assumptions pile up, and you stay on library versions that are effectively dead. No meaningful bug fixes, no security support, sometimes barely maintained at all. So freezing dependencies does not avoid the pain, it just stores it. And the longer you postpone the major bump, the more likely it is that you will eventually have to upgrade not the one thing, but a whole cluster of interdependent packages at once. Like almost anywhere in engineering, there is no silver bullet here. So we do not have tests is not really an argument against updating. It's an argument that service is already in a risk state, and freezing dependencies only makes that state worse. Still, updates may not be easy. One way to make them less painful is to keep the patch window small so you don't accumulate too much changes between versions. But the same idea is true in reverse. Any change carries risk, even rolling back. A rollback is not a free safety button. It is another production change, and sometimes it means bringing back the vulnerability you just removed. There is a great Google book I really love and recommend for everyone, Building Secure and Reliable Systems. One of its useful points is exactly this. Rollbacks represent a trade-off between security and reliability. But for most cases, updating small and is just helps a lot. So let's move from analysis to something more practical. PIP audit tells you two things. Is there a vulnerability and is there a fix? And that is already enough for a simple decision tree. If there is a fix and it's just a bump patch, like 12.1.0 and 12.1.1, then you can just update it. The breakage risk is usually low, and that is the easiest kind of win. For sure, low risk doesn't mean zero, and maintainers can make mistakes too, and sometimes even routine-looking update can break real systems. And if dependency sits on a truly critical path or performance bottleneck, you probably already know about it. Outside of exceptional cases like Meltdown or Spectre, performance rarely collapses so dramatically that a routine update turns into instant disaster. If the fix exists, but it's a minor or major bump, then you can update too, but now with a bit more care. Yes, it may take more time to actually fix the code if the backward compatibility is broken in your dependencies, but as we already know, not updating is not the real way out. It just turns today's smaller change into a larger and riskier one later. Check changelog, test it, and only then deploy. If there is no fix available, then you do not block everything forever. You unblock CI, filter the ignore, the unfixable advisory, and monitor it until something changes. Finally, if the vulnerability doesn't really apply to your context, then it becomes lower priority. And one more thing, not every developer can confidently assess the impact of every vulnerability, and that is completely normal. Sometimes the package is deep in the stack, sometimes the advisory is very vague, and sometimes you just do not have enough context to judge it alone. This is exactly why having a simple default matters. So not forget about it forever, just update when convenient. And when in doubt, update still wins. The point of this slide is not the perfect prioritization. It is that in many cases, you already have enough information to make sane engineering decision. And this is probably the most practical slide in the whole talk. Most CVs are resolved by a simple update in minutes. So keep a log file in the repository. If you're not writing tests in 2026, start now. Run pip audit regularly. First manually, then in pre-commit CI. Refresh dependencies on a schedule so update may stay small. Automate the boring part with dependabot or renovate, not because routine updates and security fixes are the same thing, they are not, but because the same tooling can help with both. The main idea is simpler. Do not wait until dependency updates become a project on their own. One more practical note, pip audit already has a GitHub action out of the box, so you can just apply it to your project. And there is an example for GitLab CI, just in case. Again, this site could be just a link to pip audit README. And one caveat here is that pip audit doesn't have fail on fixable only flag, so you need to do some filtering magic, which is officially documented in its README. And having green pipeline with unfixable vulnerabilities is practically better than having allow failure, which usually just hides the problem because it's always failing. At least then the rule is explicit instead of teaching everyone to ignore check. If CI is the enforcement point for everyone in the team, then pre-commit is the left shift. So it catches things earlier while the change is still local and cheap to fix. Pip audit has also official pre-commit support, but if you need to bypass, for example, internal packages, which doesn't have advisory, you need to apply a filter and fix. So pip audit is a great starting point, but it doesn't answer the harder questions for you. It doesn't tell you whether the vulnerable code is actually reachable, whether your deployment makes it exploitable, whether the package is malicious, or how likely real-world exploitation is. That is where developer context and often security engineering starts. Pip audit helps you see the problem, but it doesn't replace threat modeling or deeper triage. So to wrap up, 3 things you can do on Monday. First, run pip audit on your project, because it's super simple. Second, add it to CI, and third, enable automated dependencies updates. None of this replaces security engineering, threat modeling, exploitation likelihood, context analysis. That is still a separate layer. But this is developer hygiene, and it's very much our job. The security of Python service is often shaped by code we didn't write, maintainers we have never met, and decisions we inherited transitively. And maybe this is the final point of the whole talk. You cannot make the trust fully explicit just by running pip audit, but you can at least stop treating it as invisible. So run it, wire it into CI, keep dependencies moving, and please repeat it at home. So thanks for your listening, and if you have some questions, I'm ready to answer.